Apple recently announced iOS, macOS, and iPadOS 26. And one of their newest AI features is the ability for developers to access a local, offline, on-device model for simpler AI tasks. The idea is that for simple AI tasks, app can run inference locally, keeping user data private and saving money on cloud LLMs. This works fully offline, so AI apps can now work even when you're not connected to the internet. While these models are useful on their own for some basic tasks, Apple also introduced support for using custom-trained adapters with these models. Basically, these are small models you can load on top of the base model to customize its behavior and make it more useful for specialized tasks. This can vastly expand the types of tasks that these models can be used for. In this video, we will start by showing how the Apple Foundation Model Framework works and see how its results compare with other LLMs. We will then introduce adapters to see how they change these benchmarks, and lastly, go through the process of training and deploying our own adapter with Datawizz. Let's get started with the Apple Foundation Models Framework. iOS 26 makes it really simple to access on-device models. All you need to do in your app is import the Foundation Models Framework. Then you can initiate a session and send a message to that session to generate content with the model. It's really that easy to get foundation models running locally. What's the downside? These models are optimized for speed and on-device efficiency. So out of the box, they're not nearly as smart as some of the larger models you might be using, like GPT-4o or Claude 4. To put that into perspective, we ran MMLU, Massive Multitask Language Understanding, a pretty popular benchmark for language models. It's a set of 15,000 multiple choice questions in a bunch of different subjects used to evaluate the model's capabilities. When we ran this benchmark on GPT-4o, it got it right about 85% of the time. But that's a huge model that could not run on a device. Smaller models like Meta's Llama 3.2, which is a 3 billion parameter model, Microsoft's Phi-3 Mini, the 4 billion parameter version, and Google's Gemma 2, the 2 billion parameter version, all got between 50 and 60% of the test right. The Apple Foundations model got 44%. We ran a couple of more benchmarks, which I'll get to later in this video, and across almost all of them, the Apple model performed significantly worse than other small models. So it seems that even compared to other small models, Apple's built-in model is not performing nearly as well. We think this comes down to performance. Apple really wanted to make sure that running AI on device wasn't going to be slow, drain your battery, or heat up your phone. So they opted for a less powerful model that'll be more efficient to run. Now, for a lot of tasks, this model might be good enough already, but for more specialized tasks, it might not make the cut. Luckily, Apple also introduced support for model adapters that can help make this model better for more specialized tasks. So what are adapters? One common solution for doing specialized work with smaller and more efficient models is to fine-tune them. Essentially, you can train a custom model to be an expert for a specific task that your app needs. This solves the quality problem pretty well, but also means that now every use case or every app needs to load its own model. Loading a custom model for each app simply isn't feasible. Even with small models, they can still take up multiple gigabytes of space. It's not going to be a great idea for every app to load a 5 to 10 gigabyte model with it. Adapters offer a lightweight version of that. You can basically train a small adapter model, which is only a few layers deep, and load it on top of the base model. In the iOS example, the phone still has the built-in model, and the app can now load small adapters on top of it to customize its behavior and adapt it to a specific use case. This is kind of a best of both worlds solution. On the one hand, you can usually improve the outputs enough to match what you'd be able to get from much larger and more capable models. And on the other hand, the adapters are small enough to make it feasible for every app to load them. They're only about 160 megabytes in size for the Apple model. In fact, a complex app can even have multiple adapters for different use cases and tasks that it needs to run. We went ahead and created some before and after benchmarks for using custom adapters. The first test we ran used the QASC dataset. It's also a set of multiple choice questions, more about grade school science with some supporting context. You can see that out of the box, the Apple Foundation model performed significantly worse than stronger models we tested. However, when we trained a custom adapter for this task, its performance jumped, blowing other models out of the water. This shows how powerful adapters can be. In another test that we run, we use the age and use classification dataset. Out of the box, the Apple model performed slightly worse than Llama and Gemma. However, as soon as we added in a custom adapter that we trained on this data, the result jumped by 15% for an almost perfect run. Lastly, for a simple sentence data extraction task, we actually saw the Apple model performing better out of the box than other small models. It does seem like Apple really optimized the model for this specific use case of extracting structured data. As soon as we dropped in an adapter, it actually performed so well, it even beat GPT-4o and GPT-4.1. That's pretty incredible for a model that can run on your iPhone. So adapters turn out to be a super powerful feature. The biggest downside with adapters is needing to train and evaluate them. Thankfully, this is something that Datawizz makes super easy. So next up, I'll walk you through the process of training, evaluating, and deploying an adapter into your iOS app. The first step for training an adapter is getting some training data. Ideally, you want examples of the input you might send to the model and the output you expect to receive from the model. How much data you need really depends on the use case. For simple adapters, a few hundred examples might be enough. But for more complex use cases, you're probably looking at thousands or even tens of thousands of samples. If you're already using an LLM like GPT-4o in your app, there is a shortcut for getting that data. Assuming you're happy with the results you're getting from that LLM and want to train the smaller model to match it, you can just collect the logs of the inputs and outputs to that LLM and use them as training samples. Datawizz makes that collection very easy. If you're calling the OpenAI API directly from your code, you can create a new endpoint to route those requests through the Datawizz proxy and log all these requests. And as your app makes more requests, you're collecting that data and building out your training data set. Many other platforms also offer this logging capabilities. If you're using HumanLoop, Langsmith, or Langfuse today, you might already be collecting these kind of logs. In Langfuse, for instance, you can see your request logs, download them, and import them directly into your Datawizz projects. Once you have some logs imported, the first thing we recommend doing is testing out the Apple Foundation model directly. This can be a good way to check whether or not it's giving you good enough results out of the box, and if you even need to train an adapter. To do that, first deploy the Apple Foundation model to the Datawizz serverless provider in the provider screen, and then open it for manual comparison. You can also open other models to do some side-by-side comparison. We recommend trying out a few prompts just to get a feel for the model and see where you're starting from. You can also run a more advanced evaluation using the Datawizz platform. To do that, we should first make sure that we have a separate training and evaluation datasets that we're going to work with. Go to the Dataset tab. If you're importing your logs from another system like Langfuse, Langsmith, or HumanLoop, they're already going to show up there. If you use Datawizz to record your logs, we can create a dataset from those recorded logs. Once you're inside your dataset, click Create Split to create an evaluation split. 20% is usually enough to get started. This will help us make sure that we're testing the adapters that we're going to train with samples that we didn't also train them on. Now that we have that ready to go, we can run our first evaluation just to get an initial benchmark. Go to the Evaluation tab and create a new evaluation. We'll choose the Apple Foundation model as the model to be evaluated and use our evaluation set that we just created for that task. Datawizz offers a bunch of different evaluation functions we can use to test the results from our model. You can even use an LLM as judge test to create more complex evaluations of outputs. For this use case, though, we'll use the simple string equality, as we just want to make sure that the answers from the model are identical to the answers we're getting from the Apple Foundation model. Now we can let the evaluation run for a few minutes. As you can see as the results stream in, the model didn't do amazingly for our task. Hopefully we can improve that with an adapter. To do that, we'll go to the Model section and click Create New Model. Here, you'll choose the Apple model as the base model that we want to train, and choose the training data set that we just created. For the training configurations, you can just leave the defaults for now. There are a few ones that are worth knowing. Epochs, for instance, will define how many times the trainer runs over your data set. More epochs means deeper learning, but can also lead to overfitting. In our examples, Apple models did that best with about 3 to 5 epochs. Learning rate similarly controls how fast the models learn. We definitely recommend playing around with these parameters, trying out a few different combinations, and seeing how they perform for your task. It will take a few minutes to a few hours to run a training session, depending on how much data you're using. Once your training is done, You can check out the logs to see some intermittent results, and then deploy the model so that we can run a proper evaluation over it. Once the model is deployed, we can rerun the evaluation over it. To do that, I'll head back to the Evaluation tab, select the eval we ran before, and rerun it, adding this new fine-tuned adapter to the benchmark. As the results remain, you can clearly see the improvement in quality over using the base model alone. Now that we have the fully trained adapter, the last step is to use it in our application. To do that, go ahead and download the FM adapter file for your model. Back in the SwiftUI project, drag the FM adapter in. Apple generally recommends this method for testing only. In production, they recommend using asset packs to more efficiently distribute and deliver those adapter files to your users. Once I have the model here for testing bundled into my app, I can load it and then reinitialize the session with the new adapter. And that's it. Anytime you call session.respond from now on, it will run the new adapter and give you better, more precise results. So to sum it up, iOS 26 makes it easy to perform on-device AI tasks, and custom adapters make it a powerful AI platform. You can use dataset to evaluate the vanilla model and see if it's good enough for your application, as well as train custom adapters to improve its performance and customize it for your use case. We believe a lot of AI inference will be coming to the edge in the next few years, and that soon enough other phones, web browsers, and PCs will offer similar frameworks with built-in models. We plan to support those as well and make Datawizz the one-stop shop for evaluating, training, and distributing local adapters. So please stay tuned.